Welcome to Section 6 of Biostatistics. As a review, recall that we can think of biostatistics in three arms: performing the study, evaluating the study quality, and applying the study clinically. In this lecture, we will dive into applying the study by focusing on sensitivity and specificity. So let's get started. Let's say we are trying to find a good screening test for syphilis. We have test A and test B, and we have a total of 10 syphilis patients. Test B catches 2 of these patients. In other words, 2 of every 10 syphilis patients appear positive with test B. The remaining 8 test negative. Test A, on the other hand, catches these 9. In other words, 9 of every 10 syphilis patients will show up as positive with test A. This means that the sensitivity of test A is 90%, and the sensitivity of test B is 20%. So which test is better at catching syphilis? The one with higher sensitivity, or test A. So now let's focus our attention just on test A. So we caught 9 of every 10 patients, so this is relatively good sensitivity. Only 10%, or 1 in this case, showed up as negative. However, we later find that we didn't just catch syphilis patients. In fact, many patients without syphilis tested positive as well. There were a total of 15 non-syphilis patients, and of those, the number testing positive was 10, and the number of non-syphilis patients testing negative was 5. This is where we start to think of specificity. So let's draw out a 2x2 table to demonstrate this. Along the top is disease status, syphilis or non-syphilis, and along the side is test status, positive or negative. Now let's first focus on just those that were diseased. So this left half of the box. We know that there are 10 syphilis patients, so 10 will go on the bottom here so we can keep track of that. 9 of those had a positive test, so that goes up here in the top left. That last syphilis patient got a negative test, so that individual will go in the bottom left. And as we mentioned before, this gave us a sensitivity of 90%. Another way to say this is that if you have syphilis, the probability that you will have a positive test is 90%. Now let's find specificity. And we will do this by focusing just on the right side of the box, those that do not have syphilis. In our example, there were 15 patients that didn't have syphilis. So we'll put 15 right here to keep track of it. And of those 15, 5 tested negative and 10 tested positive. So we put 5 in this box, those that tested negative, and the other 10 go in the top right box. They tested positive. So to find specificity, we take the number that actually tested negative, which is 5, divided by all those who don't have the disease, which is 15. This gives us a specificity of about 33%. Another way to say this is that if you do not have syphilis, your probability of getting a negative test is 33%. Now this is what is written in your text. If you have the disease, sensitivity tells you the probability that your test will be positive. Mathematically, you calculate sensitivity by taking the true positives divided by the true positives plus the false negatives. You use a 2x2 table to plot this out. In our case, the true positives were those that had the disease and tested positive, and that number was 9. A better way to calculate sensitivity is by identifying the numerator as those that have the disease and test positive, and the denominator is simply all those that have the disease, whether or not they test positive or negative. Now for specificity, if you don't have the disease, specificity tells you the probability that your test will be negative. You calculate specificity by taking the true negatives and dividing that by the true negatives plus the false positives. And you do this by using a 2x2 table. A better or simpler way to find specificity is to look at the numerator as those that don't have the disease and test negative, and the denominator is simply those that do not have the disease, whether or not they have a positive or negative test. So let's explain the math a little more with the 2x2 table. The disease status goes along the top, and the test result is along the side. True positives are those with the disease and test positive, so they would go up in this top left corner. True negatives are those without the disease and test negative. Those would be in the bottom right. And those that don't have the disease but test positive anyways are false positives. and those that do have the disease but test negative are false negatives. To find sensitivity, we focus only on the left side of the box, or those that are diseased. Recall that sensitivity equals true positives divided by true positives plus false negatives. In other words, we take the true positive number and divide it by the number of everyone with the disease, so this entire left-hand side of the box. Now, to find specificity, we focus only on the right side of the box, or those that don't have the disease. And recall that specificity equals the true negative number divided by true negatives plus false positives. In other words, we take the number of true negatives and divide that by the number of all who do not have the disease, or the entire right-hand side column. So now let's make things simpler. To find the sensitivity, we take the true positive number, which we have written here, and divide that by all who have the disease. For specificity, we take the number of true negatives and divide that by all who do not have the disease. So let's do a question to apply this. A research group is trying to determine how valuable test X will be for diagnosing hepatocellular carcinoma, or HCC. There are 800 patients in the study. Of those, 250 have confirmed HCC. Of those diseased patients, 100 test positive with test X. The remaining participants test negative. What is the sensitivity of test X? So we are asked to find the sensitivity of test X. Recall that sensitivity is the true positive number over all those that have the disease. So let's see if we can figure out the true positive number and figure out how many patients had the disease total. So from the question stem, we are told that there are 800 total patients. And we are also told that 250 patients have the disease, which is hepatocellular carcinoma. So that gives us our denominator. The total number of diseased patients is 250. We then learn that only 100 of those 250 patients tested positive. That means 100 is our true positive number, which should be our numerator. This comes out to be 100 divided by 250. This equals 0.4, or 40%. We can reach the same answer by using the 2x2 table. We know that there are 250 patients with the disease total, so we put that down here. 100 of those tested positive. So the number of false negatives, or those that have the disease but tested negative anyways, would be the difference, which is 150. And as you recall, sensitivity can be found by taking the true positive number, which would be 100, and dividing that by the true positive number plus the false negative number. So 100 plus 150. Either way, you end up with a sensitivity of 40%. This means that test X will only catch 40% of all HCC patients. Now let's say we were asked to find the specificity of test X. Recall that specificity equals the true negative number over all who are without the disease. So how many did not have the disease in this group? Well, there were 800 total patients. 250 of them had the disease. If we take 800 and subtract 250 from it, we are given 550. These are those without the disease. So this will be our denominator. But how many of them tested negative? In other words, what was our true negative number? We know that of all the 800, only 100 tested positive. And the question stem specifically states that all 100 patients that tested positive were hepatocellular carcinoma patients. That means that there were no disease-free patients that tested positive. In other words, all 550 of these not diseased patients tested negative, and they were true negatives. So this gives us 550 true negatives divided by all those without the disease, which is also 550. This comes out to be 1, or 100%. And briefly, looking at the 2x2 table, we see that there were 550 patients without the disease, and they all tested negative. And that means there were 0 that tested positive. In other words, 0 false positives. So the specificity of test X is 100%. In other words, if you don't have the disease, the probability that you will have a negative test result is 100%. Now let's discuss sensitivity and specificity as they would appear on a graph. Keep in mind that the ideal test has 100% sensitivity and 100% specificity, but this is not realistic. Now this information down here we will discuss in a moment, but before we discuss these ideas, let's draw out a graph. On the left side, we find those that do not have the disease, and we will say that this is 80 patients. On the right side, we have those that have the disease, and we're going to call this disease rheumatoid arthritis. And we will say that this graph represents 80 patients as well. So for this example, we're going to say that our diagnostic test is the serum level of rheumatoid factor, or RF, and we will demonstrate the level of rheumatoid factor along the x-axis. And let's say we are trying to determine what serum level of rheumatoid factor will indicate rheumatoid arthritis. So let's just make some arbitrary numbers to make this clear. Let's say this point here is 0, and this point here is a level of 4, and this point here is a level of 8. Now our goal is to catch all of these rheumatoid arthritis patients on the right, and none of these patients without the disease on the left. If we set our rheumatoid factor cutoff level here at 4 in the middle, we would see that on the right, all these patients would test positive, and on the left, all these patients would test negative. In other words, a rheumatoid factor level less than 4 would mean you have a negative test, and above 4 means you have a positive test. So let's apply this to our equation for sensitivity. Remember that sensitivity equals the true positive number divided by all who are diseased. All of these patients here on the right are diseased, which is 80. Now, how many of these diseased patients actually tested positive with this cutoff value? All of them. So our true positive number will be 80. And 80 divided by 80 is 1, or 100%. Now let's talk about specificity. Recall that the equation for specificity is true negatives divided by all those who do not have the disease. So looking at the left, we see there are 80 disease-free patients. So 80 is our denominator. And how many of these patients tested negative? All of them. So our true negative number is 80. 80 divided by 80 is 1, or 100%. So this is the ideal circumstance for a diagnostic test, but reality looks a little different. This graph represents a more typical diagnostic test. Notice the overlap here. Our hypothetical diagnostic test for rheumatoid factor we said was 4, down here in the middle. So above this level of rheumatoid factor would indicate a positive test, and below this level would indicate a negative test. And we have 80 patients who have rheumatoid arthritis and 80 who do not have rheumatoid arthritis. As you can see, these patients tested negative. These would be the false negatives. Likewise, most of our disease-free patients would be negative. However, some of them tested positive, which is this group here. These would then be our false positives. So let's revisit the math. For sensitivity, we take our true positive number divided by all those who have the disease. The number of our diseased patients is still 80. However, let's say that 10 of our rheumatoid arthritis patients were not caught with this test. In other words, our false negative number is 10, which means our true positive number is 70. 70 divided by 80 is roughly 88%, which is the new sensitivity. Now for specificity, recall this is the true negative number divided by all those that don't have the disease. Now our not diseased population is still 80, so this would be our denominator. And let's say 10 of these 80 patients tested positive when they shouldn't have. So our false positive number is 10. So what's the number of true negatives? Well, it's 80 minus those 10, so 70. 70 divided by 80 is 88%. Now let's compare these findings to our previous demonstration. Without the overlap, our sensitivity and specificity were both 100%. With the overlap, our sensitivity and specificity both went down. In this case, they decreased to 88%. Now up to this point, we have had our rheumatoid factor level in the middle at 4. The reality is we can move this cutoff value of rheumatoid factor to the right or to the left, depending on how we plan to use this diagnostic test. If we move it to the left, we are catching more of our disease patients. Anything above this line would be positive, and anything left of it would be negative. And as you can see, we caught all of our diseased patients. So what will happen to our sensitivity? It will go up. Keep in mind, however, that by moving the cutoff lower, more of our disease-free patients actually tested positive. That's this group here. That means our true negative rate went down, which means our specificity went down. Conversely, if we move the cutoff value to the right and anything above this value would be positive, and anything below this value would be negative, we can see that more of our disease-free patients are actually testing negative. So what will happen to our specificity? It will increase. However, you can see that as we move up, more of our disease patients actually showed up negative, this group right here. So what will happen to our sensitivity? It will go down. We caught fewer patients, and this means that our true positive rate went down. Now, all of this can be super confusing, so let's solidify and clarify with a question. Let's say the sensitivity of diagnostic test Y is 40%, while the specificity is 100%. Which cutoff value, indicated by the yellow bar, accurately depicts diagnostic test Y? Okay, so we were told that the specificity is 100%, and recall that specificity equals the true negative number divided by all those who do not have the disease. And since our specificity is 100%, this indicates that all of our disease-free patients tested negative, and the left portion of each graph represents our disease-free patients. So all of our disease-free patients would test negative. Let's see what this would look like on each graph. Now, as we can see, only the bottom two graphs demonstrate a specificity of 100%. In other words, a true negative number of 100%. That means that we can ignore these top two options. But how do we discriminate between these bottom two? Well, let's look at our sensitivity. We are told that our sensitivity is 40%. So now that we are talking about sensitivity, we focus our attention only on these diseased patients on the right. And if the cutoff value were here, we would see that all of our diseased patients would actually show up negative. So this bottom right-hand graph would be mathematically represented as true positives over all the diseased, and the true positive number would be 0. And we know that our sensitivity is 40%. So a true positive number of 0 doesn't make sense. So we can rule out this bottom right graph. And this bottom left graph is the correct answer. And this makes sense because it shows that at least some of our diseased patients are testing positive. So it's not great sensitivity, but it's not 0. Now returning to this slide, we see that if the cutoff value is moved to the right, our true negative number goes up, which means our specificity goes up. And when you think of specificity, just think of true negatives. And if true negatives go up, specificity goes up. Conversely, as you move the cutoff value to the right, the true positive number goes down, which means our sensitivity goes down. And keep in mind that the true positive number dictates sensitivity because it's the numerator. Now, if the cutoff value is moved to the left, we would actually increase our number of true positives. And if you increase the number of true positives, you increase sensitivity. And moving left, you're actually decreasing the number of true negatives. And if you're decreasing the number of true negatives, you decrease specificity. Now let's talk about tests that can rule in and rule out disease. Now, a test that is 100% specific means that if you get a positive test, you rule in the disease. You'll often hear people say spin. The SP for specific and in for rule in, spin. A test that is 100% sensitive means that if you get a negative test, you rule out the disease. And you may hear people say snout. The SN from sensitive and the out, snout. A typical pattern clinically is to screen with a sensitive test and then confirm with a specific test. So now let's assume 100% specificity. This would mean that our cutoff line would be here on the right. Anything to the right of this line is positive and anything to the left is negative. Notice that none of these disease-free patients show up as positive. Therefore, if you have a positive test, you really do have the disease. And that's because anything that shows up to the right of this cutoff value and is positive has the disease for sure. That's this group here. In other words, you ruled in the disease. And recall spin. So now let's assume 100% sensitivity. For this to be the case, our diagnostic cutoff line should be around here. Anything to the left of this line is negative. Anything to the right is positive. So in this test that is 100% sensitive, if you actually get a negative test, you'll fall within this group, which means that you truly do not have the disease. So you ruled out the disease. And remember, snout. SN, and out, snout. And recall I said that the typical pattern is to screen with a very sensitive test, such as this one, and then you confirm with a very specific test, such as this one. Now let's do a question to apply this. Let's say you suspect one of your patients has disease K, a very rare disease. You want to be sure you don't miss it, so you order test B. The results come back negative. Based on what you know about test B, you now feel confident your patient is free of disease K. Was the test highly sensitive or specific? So our patient got a negative test, and you feel confident that your patient is free of disease K. In other words, this test ruled out disease K. And recall the mnemonic, snout. Therefore, we have a very sensitive test. Recall that sensitive tests have cutoff values low enough that they will catch most or all of the diseased patients. So somewhere around here. So our patient with a negative test result must have fallen somewhere in here. And we ruled out disease. Now let's talk about calculating false negatives and false positives. To find false positives, you take 1 minus the specificity. For example, if you have a specificity of 75%, that means that 25% of your patients are falsely positive. To find the false negative number, you take 1 minus the sensitivity. For example, if your test is 82% sensitive, that means that 18% of your patients are falsely negative. Now let's do a question to apply this. Let's say that 500 obese patients receive a screening test for hyperlipidemia. The screening test is 60% specific and 90% sensitive. How many of these patients will be falsely positive? So we have 500 patients total, and our sensitivity is 90%, and our specificity is 60%. And we are asked to find the false positive number. So on this graph, which group would represent our false positive group? So assuming this is our cutoff line, and above this is positive, and below this is negative, our false positive group would be these guys right here. Now recall the equation for false positives. It's 1 minus the specificity. Our specificity is 60%, which is 0.6, which gives us a false positive rate of 0.4, or 40%. So now we know that 40% of our patients are false positive. And we had 500 patients, and 40% of 500, or rather 0.4 times 500, is 200. Therefore, we had 200 patients show up as false positive. And that concludes this section.